So our second day of probability looks at what we call permutations and the fundamental counting principle. So what happens is, because many probability problems involve counting the number of outcomes to an experiment and event, it's important to develop techniques that will allow us to count the outcomes in sample spaces that are very large. The primary tool for this is known as the fundamental counting principle, and I'll show you in exercise 1. So if you look at exercise 1, let's consider flipping a standard coin and rolling a standard 6-sided die. So if I asked you to draw a tree diagram to determine the total number of outcomes, you would do something like I'm about to do. What I think you should do is pause and draw the tree diagram, since it's something that we did yesterday. So when you've completed your tree diagram, you can see that there were 12 outcomes. The problem is our sample spaces get really big, is that the tree diagrams get tough to make, and they get tedious, and they get messy. So if we look at part B, how could we have determined the total number of outcomes just by considering the outcomes for the coin and the die separately? Well, the coin had 2 possible outcomes, heads or tails, and the die had 6 possible outcomes, 1 through 6. And if I multiply 2 times 6, I get the same result of 12 outcomes that I got when I made the tree diagram. So oftentimes we can just multiply the different outcomes to find out the total possible. And that leads us to this fundamental counting principle. Suppose we have an event E that can be broken into a sequence of n sub-events, E sub 1, E sub 2, all the way up to E sub n. Then the total number of ways that E can occur, is given by the number of ways the first event can occur times the number of ways the second event can occur, all the way up to the number of ways the nth event can occur. The advantage of this is that the sub-events are often easier to count than the overall, more complex event. Let's do a couple. So in exercise 2, we have a cafeteria in which a student can order the daily special for $4.99 that consists of 1 drink, 1 salad, and 1 entree. If students have 5 drinks to choose from, 4 salads, and 3 entrees, how many different choices do they have for the daily special? Now you could make a tree diagram, but it would get really messy really fast. So instead, let's use our counting principle. Our first event is a drink. So we have the number of drinks times the number of salads times the number of entrees, which then is 5 drinks times 4 salads times 3 entrees, which gives me 60 possible outcomes. Imagine trying to do a tree diagram for that. Wouldn't it be fun? Exercise 3. For exercise 3, we have letters that are to be chosen from the word hyperbola without replacement to create a 4-letter code. Determine the number of these 4-letter codes that begin with 2 vowels, and here Y is considered a vowel. So I like to draw a little picture, so I'm going to draw out 4 places to be filled with letters, my code. And the first 2 digits, the first 2 parts of the code have to be vowels. Well, let's count vowels. I have a Y, E, O, and A. That's 4 vowels. So the first letter of my code has to be a vowel. There are 4 to choose from. I can't use the same one. It says without replacement. So for the second place in my code, I only have 3 vowels left. Well, let's say I use the Y and the E for those first 2 vowels. How many letters do I have left? 1, 2, 3, 4, 5, 6, 7. I have 7 letters left. I've used one of them. Doesn't matter which one. Now I have 6 left. So I have 4 times 3 times 7 times 6, or 504 possible codes made from the word hyperbola. Again, this is much faster than having to draw a tree diagram with 504 branches. Okay, on the back, we have a special application of the counting principle that occurs quite often when we count the number of ways to rearrange items from a given set. These arrangements are known as permutations. A permutation is simply any ordering of objects from a set when those objects have been chosen without replacement. So permutation is a specific arrangement or ordering of objects. Order matters with a permutation. So let's look at exercise 4. We're going to consider the letters in the word cat. We're going to make 2-letter codes out of those 3 letters without repetition of letters. So So to get an idea of what's happening, we're going to list all of the different two-letter codes. It's easy when you only have 3 to choose from. So I could start with C and get CA, or I could start with C and get CT. I could start with A and get AC, or AT. If I start with T, the choices are TA and TC. So I have 6 possible outcomes of 2-letter codes using the letters in the word cat without replacement. Well, using the counting principle, I could say, well, I have 3 letters to choose from to fill the first place. But then once I've used one of those letters, I only have 2 letters left. And 3 times 2 gets me 6. So in a little set, it really doesn't matter. But you can see what's happening here is I have 3 letters to start with, and I needed to fill 2 positions. So I multiply 3 times 2 to get me to 6. Permutations are so often used that they have their own notation. And it is the number of ways to permute n objects taken r at a time we call NPR. Now, the rule for NPR is I start with the number n, the top number, and I keep multiplying it by one number less than it. And I keep going until I get to that bottom number of factors. If you don't understand what that means, just watch these next 2 problems. So we're going to write out each of the following and evaluate them. 8 permutated with 3. That means we start with 8, and we multiply down 1 for 3 factors. So times 7 times 6. Start at 8, go down 1, 2, 3 factors. 8 times 7 times 6 is 336. 15p2. I start at 15, and I go down 2 factors. 1, 2 factors. 15 times 14 is 210. 4p4. I start at 4, and I go down 4 factors. 1, 2, 3, 4 factors. 4 times 3 times 2 times 1 is 24. You may recognize from earlier classes that if I start with a number and multiply down 1 until I get to 1, that's considered factorial. So anytime I have a permutation where the numbers are the same, it's the same as that number factorial. 4p4 is 4 factorial. They mean the same thing. All right, let's try 2 more. For number 6, I have 10 runners entered in the 100-yard dash. How many different ways could the runners finish first, second, and third? Express your answer in a permutation and as an integer. So I've got 3 places to fill. First, second, third. I can't be in both first and second or both first and third. So this is a permutation because order matters. I don't replace anything. So I'm starting with 10 runners, and I'm filling 3 places. So this is 10 permutated with 3. That means 10 times 9 times 8. Start at 10, go down 1, 2, 3 factors, and we get 720. So there's my permutation notation, and there's my integer. Last one. Darla chose 12 songs for her workout playlist. If she puts her MP3 player on random, no repeat setting, how many different orders could she listen to all 12 songs? We'll write this as a permutation using a factorial and as an integer. So she has 12 songs. She's going to listen to all 12 of them without repeating. So it's 12p12. That's the same thing as 12 factorial, which is the same as 12 times 11 times 10, going down 1 each time until you get to 1, which takes us to 479,001,600 possible ways to listen to those 12 songs. Now, of course, when the numbers get this big, we're going to be able to use our calculator, and I'll show you that next. A calculator scratchpad or a calculator page started in a new document. Push menu, and we're talking about probability, number 5. And look at our choices there. We have factorial, permutations, combinations, random, and distributions. Well, let's look at permutations first because that's what we're talking about. And notice notice it pops up NPR, that notation you saw earlier. And all you do is you enter the top number, the comma, and your bottom number. So for that last problem, we were wondering about 12P12. And there it is. There's our 479,001,600. Now if we go back to that menu, probability, factorial, it's going to say the previous answer factorial. We don't want that because that's going to multiply this number factorial. But let's take our 12 factorial just to check that they are the same. Okay. So when you're doing permutations and combinations, you'll find what you need in menu and on calculator page, probability, and there they are. That's it. Have a great night.